in terms of, like, in decimals. So in the table, I thought it would be a lot easier for you to analyze the rate of change of the whole numbers for base area than those decimals. So, but they're equivalent, which I'll show you that when we get started. But you're looking at things we've already kind of developed, and now we're making more sense out of them. And also make sure you go to that third question, that third page of question. It asks you to say what kind of function is created by these rates of change. You done? Okay. Okay, most people on that last one I'll collect in about 60 seconds.
Okay, it's the same one that we got before. Yes, ma'am. Does anybody else have their virtual day assignment and a graphic organizer? Huh?
My name's on the back.
I'll assume that they go together.
Did I put the equation in there for you too? I know. I was push you do that.
Huh? I haven't connected it, sorry.
I put in the equation for you.
Huh?
I put in the equation.
On number 3?
No, no.
Hit source search again. Should go to HTML and go see.
So you don't have to go back to mine.
Save it. Right now, and then you'll just do source search again for yourself.
Not my question, but not my answer.
Okay guys, so looking at this first table, so everybody, or most of the answers are consistent in saying that, we're adding 2 each time we increase the radius by 1, but then the differences in our responses come from, we have an additive rate of change of 2, addition by a factor of 2, let's see, we have an additive rate of change, constant additive rate of change. So how can we, between all these ideas, which one would be like the most precise to describe the rate of change in our table? Okay, so why do you say that, Kiani?
Because it's constantly adding to.
Okay, because we're constantly adding 2, every time remember the radius was increasing by 1 inch, the height was constantly adding by 2. I do want to point out, when you say addition by a factor of 2, we want to be careful when we're talking about factors here, because what do we do with factors? Okay, so typically when we're talking about factors, we're relating that to multiplication, and in this rate of change, did we have any multiplication? No. Okay, so having that constant additive rate of change would make height what kind of function? Linear. Okay, so this is all going back to the stuff we kind of learned at the beginning of the semester, but now we have more like real world examples to put it to. So then we had the second table of to analyze the rate of change from with the base area in relation to the radius. So, what did you guys notice about this rate of change? Was it constantly additive? What was it doing? Was it constantly multiplying? What was it multiplying by? So think about, what did we have to do a few weeks ago, back when we were learning about different rates of change? What were some strategies you had to apply to find different rates of change if it wasn't that constant additive? Well, what were other rates of change that we could have? So we haven't talked about cubic rates of change, we just talked about cubic functions. Okay, we've talked about linear additive rates of change. What did that look like? Or if you don't remember what that looked like, do you remember how we could find that?
No, ma'am, I do not.
Okay guys, so remember, well, when we're finding rates of change, we're looking at how am I changing from here to here?
3.14.
Well, right, so I added 1 pi, so we'll just do plus pi, 1 pi. Okay, but then from here to here, what was I changing by?
4 pi.
So to get from 1 to 4, we had to add how many? 3. Okay? And then from here to here, how many did I add? From 4 to 9.
5.
Okay, and then from 9 to 16, how many did I add? Okay, does this tell me anything?
Oh, it's plus 2.
Where do you see this plus 2 now?
From pi to 3 is plus 2.
So what Caleb's saying is we found this first set of differences didn't really tell us the rate of change, but now he can see more of a pattern between these numbers because these are going to be doing what, Caleb? These are constantly adding to. So what kind of rate of change did we have? What kind of rate of change does this give us? Linear additive. Okay, so we can see the constant additive there, and then our linear additive rate of change here, which would make base area what kind of function? Quadratic. Okay, so I see like where the confusion was here. But guys, remember, when you're looking for rates of change, you're analyzing what's different from this one to the next one, right? And if you don't find any patterns, keep going. Like you're continuously looking for patterns. Okay, and then we talked about, from, now that we know these rates of change, we can assign, like we can describe it to be a certain kind of function. So base area is quadratic, and that represents a linear function. So this, guys, is literally, okay, this is question 2, but remember where we were. We started with exploring the volume. On 3.1, we did the volume of those rectangular plank boxes, right? Length times width times height is how we got that volume. On 3.2, we started talking about cylindrical planners, and they were also calculating the volume. And so, okay, so this is our table that you have. This is the same table you have written down, except I just went ahead and wrote everything in terms of pi, but this is what I was saying, it's equivalent to the decimals that you have written down on your table and how we did it Monday. Okay, so here's asking us, so here's where you're going to want to write what we just talked about in the bell ringer, because then now we're going to talk about trying to find the rate of change of volume to describe what that means for volume functions. Okay, so under 2D, go ahead and write what we've already talked about. That height had what kind of rate of change? Okay, so a constant additive rate of change is what kind of function, KT?
Linear.
Okay. So a constant additive rate of change gave us a linear function. Okay? And then we had base area had what kind of rate of change, Tania? Base area. So we said that base area was a kind of function. Remember, so it's quadratic, meaning it's going to have what kind of rate of change? Linear additive. And remember how we can also see that in the table. So if you're having trouble remembering that, base area had a linear additive rate of change, go back to, well, I know what kind of function it is because I know what it looks like on a graph. So from that, I can determine what the rate of change is. Quadratic. Okay, so we still have to find what the rate of change of volume is. So, does anybody have any ideas?
Cubic.
Okay, well, volume's a cubic function, right? So, whenever we have like a quadratic function, did we have a quadratic rate of change? No. So if I have a cubic function, do you think I'm gonna have a cubic rate of change?
No.
Okay, so we're gonna explore and see what it is. So in your groups, I want you guys to take a few minutes. You're looking for the rate of change of the volume. So in your table, only look at row 1, 2, 3, 4, and 5. Because remember that next row, it doesn't follow the pattern anymore because we're looking for something else. Okay? So you're only analyzing the change of these rows to find rate of change for volume. But then after you do that, so number 3, so after you find the rate of change, number 3 has us graph the 3 functions separately and then kind of talk about how they all go together. So once you do that, you can start graphing them. And then we'll come back and talk about it, but don't stop after you find what the rate of change is, okay? Like, go ahead and start graphing and think about those other questions. But, so go ahead and start talking in your groups. I'm coming around, ask questions, support you guys. Yeah, go. Yes.
I don't know.
So guys, it might be useful to write the volume values in terms of like in the pi, what they are with the pi value. Okay, so like write that on your paper so you can look for the rate of change. You have something on code? So, okay, so this table talks to like this table you can put here. Okay. Yeah, so right now, okay.
It's a whole table.
Do what? Well, this one, it's similar because it's still calculating volume, but it's talking about the volume of the cylindrical planners, not the rectangular ones that we're working with in the first table. Okay? So we're still calculating volume, but we're multiplying different things here. Because remember, to get the volume of the... Do what? Alright, I'll let y'all think about that. Okay, what you seeing?
We were just trusting your
What are you seeing? What's it multiplying by? Not 14. Okay. Do you notice anything there, Sean? What do you notice about those values? Well, what's 24 times 2? Is it 36? Okay. How are you guys doing? So have you found any? Okay. So do you see any relationships between the numbers? Some of them. Huh? Well, how'd you get from here to here? Okay, and then from there to there is, well, if that's not telling us anything, what do we need to do? Well, wait, before you go to multiplication, think about, when I didn't find anything the first time, did I go to multiplication, or what did I do?
Found a rate of change between the numbers.
You do it again, okay, because find the difference of the difference, see if that can give you a more solid idea of the pattern you might be looking for, okay? Have you done that yet? So it might be helpful to me to write everything out in terms of just pi, because then you'd only be seeing what is changing between 0 and 2, and 2 to 16, instead of saying what's changing between 0 and 6, 6 and 50. But those values are equivalent, because if I multiply 2 times pi, that's 2 times 3.14, which is about 6.28, right? So that's where those values come from. So I had just rewritten them on here in pies to like help us out with this discussion and this lesson.
So the last where it's 20.
So how many times did you have to find the difference to get to that point? Twice, okay? Okay, so the fact that you had to do that again, think about what kind of function are we working with and how many times you had to do that. Think about those functions and how many times we had to find those differences to find the rate of change. Okay, compare those compare those things.
Oh yeah, the last one.
And I swear I told you to write it down in terms of pi so you don't have to deal with decimals. And I need you to write it so you can do
So
it.
you didn't go after that? You didn't write that down?
Because, so Caleb, when you write these down, you can actually, because what you're doing, because you only have the decimals on there. So
I ain't talking about after that.
you're gonna get, you can find the rate of change because they're equivalent, but you're wanting to skip some steps. Which is why I told you to just go ahead and copy this down,
So copy all that down.
copy, which one?
No.
These, so like two, what do you have in this box? Instead of 2 pi, what's written in your box? Okay, so what is 2 times pi? Yeah, round is, you're right, they're a little off, but, so do you see where these pi values are coming from? Okay.
Is it added in
Okay guys, so if you kind of already figured out like what that rate of change is, and maybe you don't know what to call it, that's okay, we'll talk about it. Go ahead and start looking at number 3 and graphing these on the graphing calculator. So that's all number 3 asks you to do is use the technology and sketch it. So you can go ahead and start doing that. You think what? Well, okay, so from here to here you did, it's 16 times 8, is that equal to 54? What did you tell me you were going to do after you took the first round of differences, first set of differences, and we didn't really see anything like a real solid pattern? What did you say you had to do again? Okay, so do it again, but keep that pattern of what is it like adding or subtracting by. Okay, don't necessarily change the operation. You know what I'm saying? To look at? Okay. Don't listen to me.
Rate of change.
Harmony.
Well, yeah.
Have y'all, so in number 3 when it says, graph and label A of x, H of x, and B of x, well, remember, what is H of x? Height, so how is that written out?
Like that.
Yeah, just put it in the equation, and you do want to graph them all in the same window, so you have to do like the double click on the inside of the graph. Yes. Okay.
Oh, that's a good.
Yeah, you could do it like that. You could also
You must be new.
do menu, show, or view, maybe. Show the grid. No, line.
Good job. Okay, last one.
So there. So when you graph them, remember you can make it show you the lines a little bit better, or like more clearly through the settings. Okay, so have you guys found?
The first one was times x squared.
Are you looking for one? Look at that first set of different. Okay, Jaquan.
Like first on this first.
2 times x, the first one.
This second.
Have y'all found that?
That's great.
Okay, so what happens when you take the first set of differences?
Hold on,
2 times x.
Well, how do you find the rate of change?
One
What do you do when you're looking for rate of change?
You don't have to put it.
Okay, so how much is it going up by
Type E.
from 0 to 2?
Oh, that's okay.
How much am I going up by from 0 or 2 to 16?
Okay, first one, 2 times x.
14, okay, and then how am I going to from 16 to 54? Okay.
No, you don't put it in
Is
the
that
third.
telling me anything right now?
The third one is.
What do I need to do? I'm not getting a solid
That's why,
pattern.
okay. So why you ask you it?
Anything constant on this first round of differences. What did I have to do to get that quadratic? The rate of change from quadratic multiplies. Dig it?
Oh, sure.
We were finding
Too much.
Okay.
Well, the
After you
pictures I
find what
seen
is
on the
from. From that, to the next. Yes. Sorry. What's up?
So after you graph.
Yeah, so after you graph it, just transfer it to shape.
Sorry, I'm not.
Up is wired.
Like after
It's going by yeah. The scale. So yes. So think about like for height is to be like y equals 2x. So it's still like if your x was like 0.5, my y is gonna be 2 times that, right? So I'd still be at 0.5 comma 1. So you're still following, like you can still plot your points based on like what the equation tells you, right? But oh, okay. Well, I mean, yeah. What's up? Do what? Go to menu. Grid. And then you probably want to do line. Yeah. Okay, so you got down to that 12. Okay, so how many times did you have to do that? Okay, so how does that, so we did 1. Well, think of it, we had to still go one more extra time than we did for the quadratic function, right? And what kind of function is this?
I think that's the worst.
So do you see, I want you to see that relationship? If you raise the degree of the function, so when I look at that rate of change, you had to do it another time to be able to get down to that, that plus 12 plus 12 plus 12 came from, like, there's where you'll see the constant additive rate of change. And then the next one is where you see the linear additive rate of change. Okay, so we're about to talk about that.
Because you know how it's on like the color. I was looking this way, like it's on the white color.
We're about to talk about rate of change. Okay guys, let me get your attention back up here. Okay, Mamar, let's look up here. So, talking about rate of change for volume. Let's see. Tamia, your group had a really good, you guys kind of got stuck at first because this group found the set of differences for these volumes. So like to get from 0 to 2, we had to add how many? 2 pi, and then from, so then from 2 to 16, how did I get there?
14.
Okay, and then from 16 to 54, how did I get there? Okay, I had to add 38. Okay, and then from here to here, what I do? Okay, so Tamia's group, they did this and they're like, I don't see any pattern between these numbers. I can't multiply, by anything to get 14 and multiply by the same thing to get 38. And I was like, well, guys, what did we do? Think about what we did when we were looking for the rate of change for quadratic functions, and we arrived at this first step where there's no relationship in these differences. Caleb, what do we have to do? You ain't forget. Do it again, right? Because I'm looking for patterns. Okay, I'm looking for patterns until I can find one. So how did I get from 2 to 14? Okay, 14 to 38. Okay, and 38 to 74. Okay, so I still don't have that constant additive thing that I'm looking for, but what did y'all notice about where when you got to this point, you did notice something coming together a little bit more, right? So what did you guys notice? Okay, so he noticed, so from 12 to 24 to 36, we're adding 12 each time. I will say, be careful. I did see people in this class and last class saying, oh, well, I do this, that's times 2, so that rate of change is multiplicative times 2. Pay attention. What's 24 times 2?
48.
Okay, it's not 36. So remember, you're looking for a consistent pattern. Don't just check the first set of values and decide, oh, that's the pattern. You gotta make sure it works for everything. Just kind of how we did when we were dealing with transformations. You can't just check the first set of numbers to see how it changed. You have to go through all of them. Okay, so then from here, is that constant additive? Okay, so well, if this is constant additive, and this is what kind of rate of change? Okay, linear additive. So, what would that make this rate of change? Quadratic additive. Why do you say that, Chloe? That's what Mr. Kenny said. So,
What?
why?
I never said it today. You're coming up with that.
So, well, this is a new, like, type of rate of change to us. And volume functions cubic functions do have a quadratic additive rate of change. Well, let's write it, and then we can talk about some connections. Okay, so cubic functions have a degree of what? 3. Where does the idea, what's the degree? What am I talking about when I ask you what's the degree of this function? Talking about what? The highest power of the, cool. So cubic functions are degree 3, have quadratic additive rates of change. Okay? Quadratic functions are degree 2 and have a linear additive rate of change. Okay, and then linear functions, so if I take another degree off, what kind of rate of change do I have? Well, it's just that constant additive rate of change. So, yes, this rate of change is new to us, but Chloe, I was really hoping you got that idea of quadratic because we were adding one each time, not just Mr. Kenny said it. But you guys can still see, like, that's where it's coming from. Okay, so moving on to this part. Have y'all graphed them yet? Or is that what y'all are doing right now? Okay, go ahead and continue that. Continue graphing them. I'm going to graph them up here while you graph them here, and then we'll talk about them, okay? Does anyone have any questions about this part? Is anyone having trouble graphing them? Okay.
I pulled on the until like there was a remark. It was like yeah, whenever I closed my eyes,
I think she's doing the first thing.
there's like a
It's like there's a number 4, it says, what does this mean?
She's doing the first thing.